Welcome back to Manish Kumar channel. So today we are interested to talk about the limits of complex function at infinity. Right, the symbol for infinity is this. So let us have a look how do we solve the limits if the infinity point is involved. So it means if you have a complex plane C, right, union, I'm going to add another guy plus infinity, right? And this is called extended complex plane, extended complex plane, right? It is often useful to augment the complex plane by including a special point called the point at infinity. As you see already denoted by the symbol, the resulting set, this set, right, consisting of the complex plane together with this point is referred as extended complex plane. Okay. To visualize the point at infinity, one can imagine the complex plane intersecting the equator of a unit sphere centered at the origin. We will see in figure 1. This geometric representation is known as stereographic projection, right? That is a very special name. So each point Z in the complex plane corresponds uniquely to a point P on the surface of the sphere, right? Specifically, P is the point where the line connecting Z and the North Pole N intersects the sphere, right? Conversely, if you see, every point P on the sphere except the North Pole corresponds uniquely to a point Z in the complex plane. It means that on the sphere, all the points, right, except North Pole is mapped to the complex plane, right, uniquely. It means that one correspondence has been established. Okay, so let us see that picture. So see here, this is my sphere, okay, and this is the North Pole, and this is the origin 0, 0, 0, assume, right? And this is your complex plane. Okay, so any point in the complex plane you are going to map through a straight line, right, which meets at the surface point P, right? You got it. So any point you can take and then you can draw a North Pole line, right? And then which meets to any point here Z1 and so on. Any point on the sphere, you can always find a point on the complex plane, right? So this is called the stereography projection. Okay. So it means that by associating the North Pole of the sphere with the point at infinity. So if you see here, this one correspondence, but the North Pole will be associated when you are reaching to infinity. Because if you see here, if you are going to find any finite point in the complex plane, right, let's say Z2, this is a finite point in the complex plane, then whenever you take a straight line, it will definitely intersect some of the point on the sphere, right? This is your P3 point. For example, Z1, this is your P2 Z1 point, and so on, right? So this is P2, right? So only the point North Pole which map to the point at infinity in the complex plane. So when Z is going to be infinity, that point anywhere if you can map is going to map to the North Pole only. Otherwise, any finite point if you are going to take, it will definitely intersect the surface of the sphere, right? So one correspondence is possible, right? One correspondence with the complex plane and the sphere of surface of the sphere. So we establish a one-to-one correspondence between the points on the sphere and the points in the extended complex plane because the North Pole is going to map to the infinity, right? And remaining point on the sphere is going to map on the complex plane. Okay, so this if sphere is known as the Riemann sphere, right? And then mapping is referred as stereographic projection. This is a very important actually. Okay, so under this projection, the exterior of the unit circle modulus z greater than 1 in the complex plane corresponds to the upper hemisphere of the sphere, excluding the equator and the north pole. Furthermore, for any small positive epsilon, right, the region of the complex plane outside the circle modulus z is equal to 1 by epsilon correspond to the neighborhood on the sphere close to the north pole, that is point n, right? So this set z belongs to C such that modulus z strictly greater than 1 by epsilon is referred as the epsilon neighborhood or simply a neighborhood, right, of infinity. Okay, so this is very important. So let us agree that unless explicitly stated otherwise, a point z referred to the point in the finite complex plane, whereas the point at infinity is involved, it will be specifically indicated, right? So only north pole is going to map to the infinity, and if you want to make any neighborhood, if you see any neighborhood, epsilon neighborhood, if you want to prepare on this surface, right, epsilon neighborhood, this is epsilon. Okay, if you want to make any epsilon neighborhood, right, so mod z is greater than 1 by epsilon, this is going to be the your epsilon neighborhood, right, for all mod z greater than strictly greater than 1 by epsilon. Epsilon is very very small, right? So this definitely becomes, this is reaching towards infinity. So and you see infinity is mapped to the north pole only because it is not intersecting any of the surface point, right, except the north pole. Okay, so you can always find a neighborhood of the point n, that is the north pole. So that is what, if you see here, so with this understanding we can meaningfully find the limit z tends to z naught fc equal to w naught. Now here the question is, even when either z naught or w naught or both are replaced by the point at infinity, right? In such cases, the standard definition of limit is modified by replacing the appropriate neighborhood of z naught and w naught with the neighborhood of infinity, right? So we are going to revise the limit definition what we have discussed. So if z naught and w naught are 2 points in the z and w planes respectively, then if I find the limit z tends to z naught fz, here w naught is infinity, right? If and only if limit z tends to z naught 1 by fz, so we have taken the reciprocal of the function, right, 1 by, and then rather than taking infinity it becomes 0, right? If and limit z tends to infinity, so here z is infinity, right, f of z equal to w0, if and only if limit z tends to 0 f of 1 by z equal to w naught. So whenever the w is infinity, we have to take the reciprocal of the function. Whenever the z tends to infinity, then we have to replace z by 1 by z, replace z by 1 by z, right? So that's how we have done in second one. Okay, and moreover the third one, limit z tends to infinity and w tends to infinity, both are infinity, right? So in the third case, both z naught and w naught are infinity, right? So in that case, what had happened, limit z tends to infinity fc equal to infinity, if and only if. So we have to take the reciprocal of both. First function reciprocal and z reciprocal. So z reciprocal is 1 by z is equal to 0. So this is the mixture of these two. Third one will be the mixture of these two. Okay. So based upon that, we will do one problem, and that is also helpful. This lecture is also helpful while calculating the residue at infinity. We will again recall these statement later. So let us observe one problem. Find limit z tends to minus 1, iz minus 4 divided by z plus 1 is equal to infinity. So here w0 is infinity. W0 infinity means what we have to do, fz will become 1 by fz, right? So what had happened, reciprocal has been taken. So what had happened, z plus 1 is in the numerator and iz minus 4 will be in the denominator, right? And then limit will be rather than infinity, we can write 0, right? When you plug it here, you will get the same, okay? And second, because z equal to minus 1, if you plug minus 1 plus 1 will be 0 basically. Numerator is 0, so overall 0. Second, limit z tends to infinity. So here z naught is infinity, right? Z naught is infinity. Second case. So 4z plus I divided by z plus 1. So in that case, is equal to 4. So how do we get? Because, z naught is in infinity. So 1 by z you have to do everywhere. So we did that. And then after that final solving this, you will get 4. Furthermore, the mixture of both are infinity, right? In that case, you have to take 1 by z as well as the reciprocal of the function. Once you do this calculation, you will get 0. So I hope you have understood. Thank you very much. Thanks a lot.